So now I'd like you to turn to Worksheet 13 to look at percent dissociation and these notes. It says, often we need to specify the amount of a weak acid that is dissociated when the equilibrium has been achieved. It's really easy. You're just going to take the amount dissociated, which is almost always going to be your hydrogen ion concentration. It could be different if it's a base, divided by your initial concentration times 100. So it says if we know that a 1 molar solution of HF has a H plus of 2.7 times 10 to the minus 2, what is the percent dissociation? Just to quickly show you, you wouldn't need to actually do this, but just to quickly show you, if you have HF becomes H plus plus F minus, and we look at a little ice chart here, we know that this is 1.0 and that this was 0 in the beginning. And if we know the hydrogen ion concentration, which is 2.7 times 10 to the minus 2, we know that that's how much, that is our X value that we've solved for. So 2.7 times 10 to the minus 2 over the 1.0 molar. And if we solve that times 100%, and I'm just a little bit out of room there, you get 2.7%. So let's try this with a problem. We're going to do A together, and then you will be able to do B on your own. And so this is your first time doing a problem without going through all the steps. So the steps should be pretty clear in your head. List your major species. So this is for A. My major species are HC2, H3, O2, and it's 1.0 molar. Pick something that can produce H plus and write the reaction. So HC2, H3, O2 becomes H plus plus C2, H3, O2 minus. Now you're going to have to, everything that I'm showing here is what you're going to need to show when you do this on your test. But we can shorten it a little bit. We can use this reaction that we just wrote to be our ice chart. And so I know that I'm starting with 1.0 molar. I know that this is 0 and this is 0. I know that this is minus X, and 1.0 minus X, X, and X. Okay? Just like on our last unit, we have to write the equilibrium expression, the whole thing. Ka is equal to H plus C2, H3, O2 minus over H, C2, H3, O2. So I need to show that equilibrium expression, and then I need to show it substituted in. Ka is equal to 1.8 times 10 to the minus 5, which is equal to X, X, and then 1.0 minus X. We're going to solve for X the easy way, and so rather than recopying it, we can just slash that through. We're not going to scribble it out or anything, we're just going to slash it out to indicate that we are eliminating it to try it out. And we're going to solve. So we end up with 1.8 times 10 to the minus 5, and that ends up being equal to X squared, because it's divided by 1. And X ends up being 0.00424 molar. Because we went ahead and made that assumption, we have to check the 5% rule. When I'm running out of room here. So we have 0.05 times the 1.0, which gives me 0.05 molar, which is greater than 0.00424. So my 5% rule checks out okay. And then the last thing I need to do, and I was trying to make this so that it would all be in one column here, is my percent dissociation. So I'm sorry I didn't leave you much room here to do your other problem. But percent dissociation is equal to 0.00424 over the 1.0. And notice this can be any beginning concentration. It just happens to be 1 for both our example up top and our example here. And it equals 0.42%. And I'm going to go ahead and have you solve for the pH so you can compare those. pH is equal to 2.37. There's an important part on the next page, an important summary, and you'll see this once you do the other problem. Results show two important facts. The concentration of the hydrogen ion is less for the 0.1 acetic acid than for the 0.1 molar acetic acid, but the percent dissociation for the 0.1 is greater than that for the 1.0. And you'll see that when you go ahead and do that calculation.